students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So today we are going to do the second part of the chapter classifications of elements and periodicity in properties. So we have already done the part 1 and today we will be discussing the most important topics, that is your electronic configuration and periodic table and trends in periodic properties. So remember, the most of the questions will be asked from this trends in periodic properties, so make sure that you watch this complete video and make note down of all the exceptions and all the trends, okay? And one more request, dear children, please join our WhatsApp channel, link is there in the description section, and this will help you to get access to our PDF notes, to our mock test solutions. Everything is available in the WhatsApp channel. Please do not forget, link is there, so go there and join, and let's start today's class with full energy. Let us go to the, so you know we are doing this chapter in two parts, okay? So one second, yeah, okay. So part 1 we have already completed, in which we discussed about genesis of periodic table, where we talked about Dauvergne triads, law of octaves, Mendeleev periodic table and modern periodic table, right? Then we discussed nomenclature rules for elements with atomic number more than 100. So in today's lecture we are going to cover electronic configuration and periodic table, electronic configuration and type of elements, and very important, that is periodic trends, okay? So let us see year-wise weightage. You can see one question you can expect every year, okay? So here in this electronic configuration and periodic table, we will be discussing electronic configuration in period and electronic configuration in group, okay? Electronic configuration and type of elements. So here we will be discussing S block, P block, D block, F block, metals and non-metals, okay? Coming to periodic trends, we are going to discuss about atomic radius, ionization enthalpy, electron gain enthalpy, electronegativity, diagonal relationship and anomalous property of second period of elements, okay? So these are the topics. So many topics are there to be discussed today. Let's get started, okay? So first of all, coming to electronic configuration and periodic table, okay? So electronic configuration in period, okay? So what is there? The period indicates the value of n for the outermost valence shell. Means suppose an element belongs to second period, okay? That means its valence cell should be second shell. If an element belongs to third period, then its valence cell is the third shell, okay? So the period indicates the value of n for the outermost or valence shell, okay? So that means in layman term I can say that the if an element belongs to second period, okay, then its valence shell must be 2, okay? For example, let us take magnesium, right? Magnesium is an element of second period, if you know hydrogen, helium, and then we have lithium, beryllium, then we have that side carbon, oxygen and all, right? So let us take the example of beryllium. Okay, beryllium is an element of second period, right? So what is the electronic configuration of beryllium? Hydrogen, helium, lithium, beryllium, so 1s2, 2s2, right? So you can see the elements of the second period beryllium, its valence cell is a second shell, right? Now let me take the example of any third period, okay? For example, we have here potassium, okay? So potassium electronic configuration, if you see 1s2, 2s2, 2p6, 3s, right? 6, 7, 8, 9, 10, 3s2 and one second, okay, one second, let me just write down the element's name. I got little confused here, so sorry students. So we have hydrogen, then we have lithium, then we have sodium, and then we have potassium. So this is first period, second period, third period, right? So second period if I take, that is your we have here, that is first period, second period, third period and fourth period, right? So if I now write sodium electronic configuration, you see 1s2, 2s2, 2p6, right? So 6, 7, 8, 9, 10, and then we have 3s1. So you see sodium is belonging to the third period and its last shell is 3s, right? So similarly, whichever period the element belongs, its last electron enters to that particular shell. Okay. Now coming to the electronic configuration in the group, so that is very, very important. Elements in the same vertical column or group have similar valence cell electronic configuration, the same number of electrons in the outer orbital and similar properties. Okay. So now suppose if you see, we have just suppose we compare here lithium, sodium and potassium electronic configuration. Okay, so we can understand the difference here. So I'll write here lithium, sodium and potassium, right? This is second group, this is third group, and this is second period, third period and fourth period. Okay, so lithium is having atomic number of 3, this is 11 and this is 19. Right. So if I write the electronic configuration, here it is 1s2, 2s1, here it is 1s2, 2s2, 2p6 and 3s1, and here for potassium it is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1, right. So what is you can see here is, the first point I think is very clear. This element belongs to second period, so its last electron is in second shell. This element belongs to the third period, so its last electron is in third shell. This element belongs to fourth period, so its element is in fourth shell, right. Now the question arises along the group. Along the group, if you see, the valence electronic configurations are similar, that is they have only 1 electrons in their last shell, 2s, 3s, 4s, right. So that is why their chemical properties along the group or down the group will be same. Clear? Next, coming to electronic configuration and type of elements. So the whole periodic table is divided into 4 blocks: S block, P block, D block and F block. So if you see first about S block, here the last electron enters the S subshell, okay, and it has 2 groups. This is very important. So these 2 groups are with elements having outermost configuration NS1, that is alkaline earth, alkaline metals, and NS2, that is alkaline earth metal. So here we have group 1 and group 2 of periodic table belongs to S block. Okay, these elements are highly reactive metals. The compounds of S block elements are generally ionic in nature. Okay, so very important thing here. Next, coming to P block. Okay, so group 13 to 18 elements are known as P block elements. The differentiating electron, or you can say the last electron, enters into the P subshell of the outermost energy level. Okay, the electronic configuration varies from NS2 to NP1 to 6, means it can be NS2 NP1, NS2 NP2, NS2 NP3, NS2 NP4, 5 and 6. So example, if you see here, we have group 13, group 14, group 15, group 16, group 17 and group 18, right. Here we have boron, here we have carbon, nitrogen, oxygen, then fluorine and then neon, right. So if you see the electronic configuration of boron, atomic number is 5, here 6, here 7, here 8, here 9 and here 10, right. Now if I write the electronic configuration, it is 1s2, 2s2, 2p1, right. And for oxygen, for carbon, it is 1s2, 2s2 and 2p2. Here it is 1s2, 2s2 and 2p3, and here it is 1s2, 2s2 and 2p4. Here it is 1s2, 2s2 and 2p5, and here it is 1s2, 2s2 and 2p6. So here you can understand how the electronic configuration is varies from NS2 to NP1, NP2, NP3, NP4, NP5 and NP6. Okay, that is the first point here. The P block elements can contain metals, non-metals and metalloids. Okay, so metals, all of you might have studied in your 10th class. Non-metals, you know, metalloids are those which have the properties of both metals and non-metals. Okay, the group 18 elements are the noble gases. Okay, so group 18 elements here, they are called as noble gases. Why? What is the reason? Because they have fully filled orbitals. Okay, fully filled orbitals. You can see the last shell is fully filled. Okay, now here there are some special name for group 16 and group 17. So group 16 is called as chalcogens. Okay, and group 17 is called as halogens, or sometimes it is also called as pnictogens. Please remember these names. Okay, chalcogens and halogens, or sometimes pnictogens. Okay, next coming to here, here one very important thing, the S block of the periodic table and P block of the periodic table are together called as representative elements. Okay, fine. Next coming to D block. So group number 3 to 12 are called as D block elements. Okay, they are in the middle of the periodic table. Here 1, 2 and then 13 to 18. In between we have 3 to 12. Okay, now the differentiating electron enters D subshell of the penultimate shell. Okay, so that means it enters to the D subshell. That is why it belongs to D block. Okay, the general electronic configuration of these elements is n-1, D 1 to 10 and ns2. These elements are also known as transition elements. So you remember the S and P block elements are called as representative elements and D block elements are called as transition elements. Okay. Now the properties of D elements are in between the S block and P block. That is why they are called as transition elements. Okay, next the elements zinc, cadmium and mercury has completely filled D subshell and do not show the properties of transition metals. Okay, so now here if you remember, if you go to in class 12 you have studied D and F block. What is the meaning of transition elements? They should have unpaired D electrons either in the ground state or in the common oxidation state, right? But zinc, cadmium and mercury do not have unfilled D orbital or partially filled D orbital. They always have completely filled D orbitals. That is why they are not a part of transition elements. Okay, they are a part of D block elements, but they are not transition elements. Okay, so how can you define transition elements? So transition element, okay, transition elements are those which have partially filled D orbitals either in the ground state or in the excited state. Okay, clear? Fine. Next coming to F block elements. So F block elements are the differentiating electron enters the F subshell of the anti-penultimate shell. Okay, F subshell, it enters the F subshell. Now see, what is this anti-penultimate shell? See, the outermost shell is called as valence shell. Okay, the N shell. The n-1 shell is called as penultimate shell. Penultimate shell. The last one or the next one, n-2 shell, is called as anti-penultimate shell. Okay, so what happens here? The last electron enters to this n-2 orbital. Okay, that is why we call it anti-penultimate shell. Now what happens? This block of elements is separately placed at the bottom of the periodic table in 2 rows. Okay, so we have done S block, we have done P block, in the middle we have D block, and these F block elements are placed below the periodic table. Okay, the first row below the periodic table in 2 rows. Okay, the first row is called as lanthanides and the second row is called as actinides. Okay, now these elements are also known as inner transition element. Okay, these elements are also known as inner transition elements. Next, the general electronic configuration of the element is n-2 F1 to 14, n-1 D0 to 1 and ns2. Okay, so yes, that is all about the electronic configuration and type of element. So by seeing the electronic configuration you can easily say whether it is an S block or P block or D block or F block, because the last electron will enter to that particular block. Okay, clear? So now we will go to the next topic, that is metals, non-metals and metalloids, right? So metals are found on the right side of the periodic table, non-metals are found on the left side of the periodic table. Okay, metals properties and non-metals properties you already know. I do not want to discuss much about that. You know, metals have good conductors, they are lustrous, they have sonority, malleability, ductility, right? These all things we have already studied in our lower classes. Now this is very important here, which are the metalloids. So there are different sometimes conflict arises about some like especially antimony, whether it is a metalloid or metal. So in NCERT these 5 elements are given, so that is what you need to follow. Okay, so we have silicon, germanium, arsenic, antimony and tellurium. Silicon, germanium, arsenic, antimony and tellurium. Okay, these are the 5 elements which are considered as metalloids. Metalloids means they have the properties of both metals and non-metals. Okay, fine. Next we'll go to the third topic, very important topic, that is your periodic properties. Okay, so periodic properties, the first topic is your atomic radius. So along the period what happens? Along the period the atomic radius decreases. Why? Because of increase in effective nuclear charge. Okay, so as we move along the period the nuclear charge increases, and the same there is electrons are added to the same shell, right? Electrons are added to the same shell and their nuclear charge is increasing, so that is why the size decreases. Okay, now let us understand this in little detail. Suppose you have here nitrogen, okay, then oxygen, and then you have fluorine, right? So if you see the electronic configuration of nitrogen, it is 1s2, 2s2 and 2p3. Here it is 1s2, 2s2 and 2p4, 1s2, 2s2 and 2p5, right? Atomic number of nitrogen is 7, here it is 8 and here it is 9. Okay, so now just imagine what is the condition. Here we have inside the nucleus we have 7 protons are there, and in the outermost electron there will be 3 electrons. Okay, now if you see in the next one, here we have again 8 electrons, 1 2 3 4 5 6 7 8 protons are there, and in the outermost we have 4 electrons. And if you see here 1 2 3 4 5 6 7 8 9, we have 9 protons and outermost we have 5 electrons, right? Now what happens is, you see, because the number of protons are increasing, the electron, you see the here this is also 2p, this is also 2p and this is also 2p, right? So if it is 2p, that means it will be at a fixed distance from the nucleus, right? So now what happens here, due to 7 protons it will attract the 1 electron, right? But here what happens, there are 8 protons, so definitely the attraction will be little stronger. Now if you see here there are 9 protons, right? So definitely attraction will be much more stronger than this one. So when the attraction is very strong, what will happen? It will pull the electron towards itself. When the electron is pulled towards itself, the size of the atom shrinks. Okay, so that is why when we move along the period, the effective nuclear charge increases, and that is why the size decreases, right? So along the period size decreases, reason effective nuclear charge increases. Okay, next this Z stands for effective nuclear charge. Okay, now coming to down the group. Okay, so let us consider about down the group. So we'll take group 1 element, suppose lithium, sodium and potassium, right? So if you see, let us write that and check. Okay, 1 second, let me erase this one. Okay, so now if you see, we have here lithium, sodium and potassium. So lithium atomic number is 3, sodium is 12 and 11 and potassium is 19. Okay, so lithium we have what, 1s2 and 2s1, sodium is 1s2, 2s2 and 2p6, and 3 here it is 1s2, 2s2, 2p6 and 3s1 3s2, 3p6 and 4s1. Okay, so now you see what happens in lithium. Okay, lithium we have 1 second shell. In sodium we have 1, 2, third shell. In this one, potassium, we have 1, 2, 3, fourth shell, right? The outermost electron, he is very far away from the nucleus. Here it is somewhat far away from the nucleus, and here it is very close to the nucleus. Now when this one is very far from the nucleus, the force of attraction will be less, right? Distance is more, force of attraction will definitely be less, and if that is less, what we can say that the size is increasing, right? So down the group the size increases. Why? Because you see here 2s was there, then here one more shell is added, here one more shell is added, right? But in period what happens? The new shell is not added, okay? But here also you may think that, okay ma'am, here also there are 3 protons, here we have 11 protons, and here we have 19 protons, right? Number of protons is increasing. It was increasing in case of period also, but when that in the period the shell was the same, right? So that is why distance remains same, so more force can be applied. But here what happens? Although this one is increasing, but electron is moving also far away from the nucleus because new shells are added, right? So that is why here what happens, as we go down the group, the size increases due to the new shell added. Okay, fine. Now coming to about the atomic radius. So atomic radius, what happens? You can see along the period it decreases, and if you see here it is along down the group. So fluorine, chlorine, bromine, iodine, it is increasing. Lithium, sodium, potassium, rubidium, cesium, it is increasing. Okay, so that is the size. Okay, next here coming about ionization enthalpy. Okay, so I know all of you must be knowing the definition. Okay, I'll be talking about this ionic radius after this. Okay, let me first complete the definition. So amount of energy required to remove an electron from the outermost shell of the neutral isolated gaseous atom. Okay, so when you want to remove an electron from a neutral isolated gaseous atom, the valence electron you want to remove it, how much energy you need to provide for that, that is called as ionization energy. Okay, so because here you are providing energy, so definitely the process must be endothermic. Okay, now there is one more thing, IE2 is always greater than IE1. Now what is that? Suppose you have already removed one electron. For example, let us take the example of oxygen. Okay, so what is the electronic configuration of oxygen? We have 1s2, 2s2 and 2p2, right? So you have already removed, suppose you removed one electron, so it will become O plus. Okay, one electron you removed, so we will require 1s2, 2s2, now we have 2p1. So here what we had, 8 electrons and 8 protons. Now in this case we have 8 protons and 7 electrons, right? So now these 7 electrons will be held more tightly than these 8 electrons, right? Because we have more number of protons now. So removing this electron now will be very, very difficult because the number of protons are more, electrons are less, so these electrons are tightly bound to the nucleus, right? So next, this is suppose your IE1, and now you want to remove an electron to get it O2 plus 1s2, 2s2, right? So this is IE2. So definitely the value of IE2 will be much, much more than IE1. Now generally from oxygen or electronegative atoms, we should not be able to remove that, but that is just I'm giving you an example. Okay, so that is very important. IE2 is greater than IE1. Okay, now coming to the factors affecting ionization enthalpy. Okay, this is very, very important. First is atomic size. Now just imagine if you are having a very big atom. Okay, so nucleus, the last electron will be very far away from the nucleus, right? So the force of attraction will be very less, so removing an electron will be easier, right? But if the size is small, the last electron and the nucleus distance is very less, that electron will be tightly bound to the nucleus, so removing that last electron will be difficult in this case. Yes or no? Think again, let us think again. We are having a very big atom. Last electron is present here, nucleus is present here, distance is more, force of attraction is weak, so this last electron is not held tightly with the nucleus, so it is easy to remove this last electron. Now imagine we have a small atom. The nucleus and the electron are present at this distance. They are very tightly attracted towards each other. So removing this electron will be very, very difficult, right? So what we can say then, if the size increases, then ionization energy will decrease, right? We can easily remove it. We do not want more, we do not have to put more energy here. So if size increases, ionization energy will decrease, and vice versa. Okay, next factor is nuclear charge. Now see, if the nuclear charge is very high, that means what? The electron will be tightly bounded to the nucleus. Okay, so if electron is tightly bounded to the nucleus, then you need to put more energy to remove that electron, right? So that is what nuclear charge, if it increases, then ionization enthalpy will increase. Okay, next factor, screening effect. Now what is the screening effect? See here, understand it carefully. When we have a nucleus, okay, and we have this valence electron, right? Now in between this also there will be electrons present, right? Now what happens, these electrons present in between the nucleus and the valence electron, what they do, they act as a shield. Okay, they shield the nuclear charge. They shield the nuclear charge, okay? They shield the nuclear charge to reach the last electron, okay? They shield the nuclear charge to reach the last electron. So that means what? Suppose imagine that these are not there, okay? Just imagine, suppose this is the case, okay? This is not there. In that case, what will happen? These nuclear force will reach the last electron, okay? But now what happens, suppose you have so many electrons present in between here, suppose you have so many electrons present here, okay? Now what will happen, this force, nuclear force, cannot reach the last electron, okay? It will reach very what I'll say, very mild, or the nuclear force will be decreased when it reaches the last electron. So this shielding of the nuclear charge to the last electron is called as screening effect. Now if this shielding is more, okay, screening effect is more, that means what? If screening effect, I'm just writing like this, if screening effect is more, then nuclear charge will be less, means this electron will be less tightly held with the nucleus, right? This electron will be less tightly held with the nucleus, and it is very easy to remove this electron, right? Very easily we can remove, because it is not held tightly with the nucleus, because we have screening effect here. So if screening effect is more, then ionization energy will be less. Screening effect increases, then ionization enthalpy will decrease, okay? Next is type of electron. So see, suppose we have electron in 2s and in 2p. Okay, first let us talk this one. Yeah, 2s and 2p electrons are present, okay? Now this 2s is more closer to the nucleus. 2s is more closer to the nucleus, that means it is more attracted towards the nucleus. So removing an electron from 2s will be difficult than removing an electron from 2p. So what will be the order? S, P, D, F, okay? So if s electrons are present, that is ionization energy is more here, and if f orbital is present, ionization energy will be less here. The next very, very important is your electronic configuration. So whenever we have any half filled or fully filled configuration, okay, ionization energy will increase, okay? So what we can say, one second, okay, first one second. Okay, so electronic configuration, so any half filled or fully filled, the ionization energy will increase, okay? So here what I want to say is, in general, what is the trend of ionization energy? So let us discuss that. In general, so we can say that in general, okay, there are some exceptions we'll discuss. In general, along the period, okay, along the period size is decreasing, right? If size is decreasing, then ionization energy will be increasing in general, okay? Next, if you see down the group, okay, Down the group, what happens? Size is increasing, so that is why ionization energy will decrease, right? Ionization energy decreases down the group, and along the period it increases. Okay, fine. Next we have factors. We have already discussed all the factors. Okay, now coming to the exceptions. Okay, some exceptions that we have studied here. So now if you see, the first exception is beryllium and boron. Now see, in the second period, what is the element? We have lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, right? These are all elements along the period. Now along the period, what happens? Size decreases. That means ionization energy should increase. So what should be all the order? Lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, right? Now if you see but there is an exception here. Okay, what is that exception? It says that lithium, then we have boron, and then we have beryllium, carbon, nitrogen, oxygen and fluorine. Okay, here is the exception. Beryllium is having more electronic, or you can say more ionization energy than boron. What is the reason here? Now if you see the electronic configuration of beryllium, it is 1s2, 2s2, and here it is 1s2, 2s2 and 2p1. So just now we discussed that to remove an electron from 2s, okay, it will be very, very difficult. If you are comparing 2s and 2p is there, then removing electron from 2p will be easier than removing electron from 2s. Why? Because 2s is more closer to the nucleus, right? Just now we discussed the fourth point, type of electron. So this electron is in 2s, this electron is in 2p. So it is more difficult to remove this electron. Okay, so that is why what happens, electron is removed from 2s orbital, and that is why boron is having more beryllium is having more ionization energy than boron. The size factor here is dominated by the type of electron factor. Okay, similarly here one more exception is there, nitrogen and oxygen. So if you see along the size, oxygen should have more than nitrogen, but not. Here also there is an exception, and the exception is like this, that oxygen and then nitrogen comes. Okay, so nitrogen has more than oxygen. What is the reason for this one? If you see nitrogen electronic configuration, it is 1s2, 2s2 and 2p3, right? And there is something special about this 2p3. So if you see p orbital, it has 2p3. What is this? This is exactly half filled, right? And we just discussed in the fifth point that half filled configurations are very, very stable. So to remove the electron from this half filled configuration of nitrogen, it requires a much more energy than removing an electron from oxygen. So that is why what happened, oxygens come here and nitrogen comes here. Okay, so that is nitrogen has half filled stable configuration. Okay, clear the exceptions of ionization enthalpy. Okay, we'll go to the next trend here, that is electron gain enthalpy. So what is the definition here? Amount of energy released to add an electron to the outermost shell of the neutral isolated gaseous atom. Okay, so this process is generally exothermic. Whenever you add one electron to the isolated atom, neutral gaseous isolated atom, when you add one electron, the energy is released. Okay, and that is why electron gain enthalpies are generally exothermic. Okay, next what happens, EA2 and EA3 will be positive. Now see what happens, you have one atom and you added electron 1, you added to this one. Okay, now when you added this electron, this atom has become now negatively charged. Okay, because it has one extra electron, it is negatively charged. Now if you want to add one more electron, if you want to add E2 now, which is also negative, and the atom is already negatively charged, and you want to add one more negative electron, negative repulsion is there, right? So in that case, if this electron is added, in that case energy is not released. In that case you need to provide energy to add E2 to the already negative atom. Okay, what I am saying, let me repeat it again. There was a neutral atom, you added the first electron to it, energy released, the atom became now negative. Why? Because you added one extra electron. Okay, so suppose for example, let us take the example of oxygen. Okay, okay, now suppose you see we have oxygen. Okay, Oxygen electronic configuration is 1s2, 2s2 and 2p2, right? So what I did, you see we have 2p2 here. Okay, so this shell is vacant, this orbital is vacant. I added one new electron here. Okay, so now what it became? It became O minus. Okay, now I want to add another electron to make it one more electron here I want to add, right? So the configuration is correct. Oxygen, sorry, 2p4, sorry, yeah, so 2p4 was there, so I'll write it in different colors so it will be clear. So okay, so oxygen, this is 2p, okay, and already it has 4 electrons, 1, 2, 3 and 4. Now I added one more electron that I am showing with a different color. Okay, I added one more electron, it became O minus. Okay, now I want to add the second electron to make it O2 minus. Okay, so in this case what will happen? 1, 2, 3, 4, and I want to add one more electron. If I want to add one more electron here, you need to provide energy. So that process will always be positive, means you can say endothermic. Okay, next coming to group 17 elements. Okay, the halogen family elements has high negative electron gain enthalpy, means when electron is added to the group 17 elements, they release a lot of energy. Okay, very high negative electron gain enthalpy. Now what is the reason for here? If you see, they have 7 electrons in the valence shell, right? So if you add one more electron, they will get 8 electrons in the valence shell, which is a noble gas configuration, right? So they will get a stability. So they very eagerly they want this last electron to be added, one more electron to be added to their outermost shell. So when group 17 electrons to group 17, if you add an electron, a huge amount of energy is released. Okay, now if you talk electron gain enthalpy becomes more and more negative as we move from left to right along a period. Okay, so now you see along the period what happens, the size is decreasing, right? So it becomes very easy to add the electron because nuclear charge is increasing, effective nuclear charge is increasing along the period. So when you add one electron, it becomes easy to take that electron along the period, right? So if along the period size is decreasing, it is easy to get one electrons. So that is why electron gain enthalpy becomes more and more negative as we move along the period. Okay, next coming to so more negative increases along the period. Okay, so it becomes more and more negative, less negative down the group. Now if you see down the group, the size is increasing, right? The nuclear force, the nuclear charge and the outermost electron or the outside electron is, the force of attraction is very less. So that is why here energy released will be very less, it will decrease. Okay, less negative, and this side it will become more negative. Okay, now here there is again 2 exceptions. Electron gain enthalpy of fluorine is less than chlorine and oxygen is less than sulfur. Okay, these are very important exceptions. Let us understand that. So now you see, okay, just let us try to understand. Okay, so what happens, what we said that we have fluorine and then we have chlorine, here oxygen and here sulfur. Now fluorine size is smaller, right? So it will be easy to add one electron here because the force of attraction will be very easy, very high, right? So the expected was here more energy should be released, here less energy should be released, but opposite happens. Now what is the reason for that? So there are 2 important reasons here. First one is the size of fluorine. Okay, the size of fluorine is very small, due to which what happens, there is inter-electron repulsion. Inter-electron repulsion. Okay, size of the fluorine is very small, due to which there is inter-electron repulsion, and that is why we can do this. Okay, that is why the electron gain enthalpy of chlorine is more than fluorine. The same thing happens for oxygen and sulfur. Oxygen size is very small, so adding one electron becomes very difficult because the size of oxygen is very small. Inter-electronic repulsions are more. So this inter-electrons of oxygen do not allow an outside electron to come and join here, right, because there is so much repulsion present because of small size. If you compare chlorine, the size is bigger, the electrons are far away from each other, so they are not repelling the outer electron much, so it is easy to take the electron there. So that is why the electron gain enthalpy for chlorine and sulfur are more. Okay, fine. Now we'll go to the next, that is electronegativity. Electronegativity increases along the period, the negativity increases, and down the group electronegativity decreases. Okay, next very important topic is about diagonal relationship. Okay, we'll understand what is diagonal relationship. Now see, diagonal, one second, we have explained here in detail, so we'll talk here. So now see, diagonal relationship is a phenomenon observed in the periodic table where certain elements in the second period, okay, lithium, beryllium, boron, show similarities in their properties with elements in the third period that are diagonally positioned, magnesium, aluminium and silicon. So before we check that, okay, let us imagine the periodic table and think. Okay, now I have not given you periodic table photo here so that we can draw the elements and try to memorize the position of the elements. So we have in the second period, we have lithium, beryllium, then here D block will come, then we have boron, carbon, nitrogen, oxygen and fluorine. Okay, now if I write the third period elements, okay, sodium, magnesium, aluminium, carbon, after that we have silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine. Okay, so these are second period and third period. Now what happens, they are saying that in diagonal relationship the properties of lithium and magnesium will match, beryllium and aluminium will match, and boron and silicon will match. Okay, so that is what is given here. Now example, you can see lithium and magnesium, right, we have written there lithium and magnesium. So what are the similarities between them? So lithium and magnesium can form nitrides. Okay, you can see both of them can react with nitrogen and form nitrides, whereas other like they have similar properties in this case, and both form stable covalent organic compounds. Okay, they form stable organic compounds as well. Next, if you see, we have beryllium and aluminium. So beryllium and aluminium, both the oxides, their oxides are amphoteric in nature. Now what is amphoteric oxides? Means oxides can be either basic or acidic, right? Amphoteric means they can have both basic and acidic properties. Okay. Example, you can see BON, L2O3, and they can form complexes as well. Okay, so you can see beryllium can form BeF42 minus, AlF6 3 minus. Okay, next last example was boron and silicon, right? So you can see they both form covalent hydrides. The hydrides of there are generally covalent, and both form acidic oxides. Okay, so boron and silicon form acidic oxides, your beryllium and aluminium form amphoteric oxides. Okay, so these are the similarities between the diagonally related elements. Okay, next we'll go to the next topic, that is anomalous property of the second period elements. Okay, so this is something very important. Next, first you will understand here the elements of the second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. So there are 8 elements here, right? Often, so 7 elements, the group 18 elements are not considered, often show significant deviation from the expected trend in their respective groups. So generally the elements in a particular group have similar properties, okay, but these first elements of every group has something different property than their other elements of that particular group. Now why this behavior is called as anomalous behavior, and it is attributed to their unique characteristics. So something unique is present in the elements of the second period, which is why they behave very differently from the other members of their group. So what are these reasons? So you can see reason is their small size, their absence of d orbitals, okay, because they have only 2s and 2p, right, there is no d orbital, and high charge to size ratio. Okay, now we will understand what are these different like we told that okay, they are having some different properties. So what are that different properties that only the second period of a group can show? So what are that different properties? The first one here is lithium and beryllium, okay, form compounds with pronounced covalent character. Okay, lithium and beryllium both are metals, right, and metals generally form ionic compounds, we have seen in the starting. But here what happens, lithium and beryllium can form even covalent compounds. That is the first anomaly behavior they have. The second, you can see the maximum covalency of the first member of each group is 4. Okay, example, boron can form Bf4 minus, whereas the other members of the group can expand their valence shell to accommodate more than 4 pairs of electron, example aluminium. So this is why this is happening, because of absence of d orbital. Why this one is possible? This one is possible because of their small size and high charge ratio. Okay. Next, if you see, the first member of the p block elements display greater ability to form pi bond, multiple bond to itself, like C triple bond C, N triple bond N, and to other second period elements like CO, CN and CN, NO, compared to the subsequent members of the same group. Okay, so the second group elements can form multiple bonds, they can form covalent bonds, and they can have covalency of 4. Okay, so these are the anomalous property and the reasons are given to you. Okay, fine. So we are done with this chapter. All the important exceptions, periodic trends we have discussed. Now it's time to practice some questions. Okay, so first is, this was a homework question. The horizontal rows in the Mendeleev periodic table were called as periods. Okay. Next, the correct order of first ionization enthalpy of the given element is. So you can see here we have lithium, beryllium, boron and carbon, right? We have studied the exception here. We should not do any mistake in this particular question. If you see, the order should be lithium, then beryllium, and then boron and carbon, right, according to the size. But boron comes before beryllium, so this is the correct order. Okay, now what is the reason? Here the electrons has to be removed from 2s, and here the electrons has to be removed from 2p, right? So that is why here the correct answer will be lithium, boron, beryllium, carbon, option number A. Okay. Next question here is, the property of halogens which is not correctly matched is as, okay. So if you see iodine, bromine, chlorine, fluorine, okay, density depends on mass, down the group mass will increase, so density will increase, so this is correct. Electronegativity decreases down the group, so this is also correct. Ionization enthalpy decreases down the group, this is also correct. But electron gain enthalpy, sorry, here it is not electronegativity, it is electron gain enthalpy. Okay, sorry, one second. Okay, so electronegativity is correct, but if you see electron gain enthalpy, we just discussed one exception, that fluorine is less than chlorine and oxygen is less than sulfur. Why? Because of small size. And due to this small size, what happens? Due to this small size, we have inter-electron repulsion, right? So option number C will be the correct answer. Okay, fine. Next we have element X, Y, Z have atomic numbers 19, 37 and 55. So if you remember, 19 is potassium, right? And if you add 18 to this one, we get 37, right? So next element, lithium, sodium, potassium, we have rubidium, right? And then if you add another 18 here, we get 55, right? And that is your cesium. Okay, which is the following statements true about? So these all elements belongs to group 1, right? Okay, Z, so this is your X, this is Y and this is Z. So Z would have the highest ionization potential. No, down the group ionization potential decreases, so Z will have least, so this is wrong. Y would have the highest ionization potential. No, X will have highest, so that is also wrong. Their ionization potential would increase with the increase in atomic number. Ionization potential does not increase in atomic number, right? It decreases with the increase in atomic number. This is also wrong. Y would have an ionization potential in between of X and Z. Yes, that is correct, because the order is like this: X, Y and Z. Okay, so correct answer is option number D here. Okay, next question, amphoteric oxide among the following. So we have discussed this, I think, beryllium. So if you see in the anomalous property, we have written here, yeah. So you can see beryllium and aluminium form amphoteric oxides, right? So BeO is the correct answer to that question. Let me go to that question. Yeah, so option number C is the correct answer. Next, the third ionization enthalpy is highest in. So the third ionization enthalpy will be highest in the alkali earth metal, because you will be removing electrons from a fully filled shell. Okay, fine. So that was this, and this is a homework question now. The first ionization enthalpy of the following state elements are in the order. So remember the exception and do this question and do comment down the answer. Okay, so students, thank you for watching, and if you are enjoying, if you have any problem, if you need any help, please do comment down. We'll definitely address it. And remember your target, that is 60 out of 60 in KCET Chemistry 2025 series. So yes students, please work out, and this is the time to be really serious about your preparation. So please do not get diverted, do not get distracted. Just 5 months, put all your efforts, and definitely you will get that 60 out of 60 in KCET Chemistry. So today, once again, let us remember our target. So those who want 60 out of 60, please comment down. Let me see how many of my students are ready for this. Okay, thank you, and you will be getting this PDF in the WhatsApp channel, so do not forget to join. And one more time, please remember your target, and see you soon in the next class very soon.